the alternating series remainder. So I mentioned this on Thursday, that the one type of series that we are going to look at the remainder in some detail is the alternating series. And so in the big picture, when you have a series that converges, it's nice to know sort of how fast it's converging. It's nice to know if you go at 1,000 terms, how close are you to the actual sum? So if we've got this series that converges to S, we don't want to have to use an infinite number of terms if we're out in industry doing stuff. We want to use the least number of terms that gets us to an accurate enough result. So we have to be able to analyze the remainder in general. And that can be complicated for a general series. So we're going to sort of explore the idea through the alternating series and look at the remainder. So in order to understand this right here, we need to look at a couple of pictures. So first off, let's take a look at a series that is alternating. And so what I want to first have you think about is that the sum of the series is going to be its partial sum plus the remainder associated with the partial sum. So if we look at, say, S sub 5, so our series, let's just write it out in expanded form. We're thinking about our series looking like this. And this isn't even an alternating series, I'm just looking at this series, just any general series. If we say that this right here is S sub 3, then we're going to call the rest of the series R sub 3. So S sub 3 is the sum of the first 3 terms. R sub 3 means whatever's left. It's the sum of the tail where you chop off the first 3 terms. Okay, so we're thinking of any series that converges can be broken up in this way. And so then they isolated R sub n in this theorem up here and said, oh, well, we can just say that the R sub n remainder is just the sum of the series minus the partial sum S sub n. Okay, so that's just sort of general perspective on series that converge. So that's the terminology. R sub n is going to correspond to the remainder for S sub n. All right. Now, the key with the alternating series is understanding this picture. So first off, notice that we have S right here. So S is this horizontal asymptote, if you will. It is the sum of the series. And if we have an alternating series that converges, every time we add a new term, we bounce through that eventual sum. If we add, and then we're going to add a negative and go down below, and then we're going to add a positive and go above, and then we're going to add a negative and go below. So we're going to be sort of bouncing or oscillating around the actual sum of the series. So what I want you to notice is that here is S sub n. It's above the sum of the series. So when we get to our next partial sum, we're going to be below. So this distance right there is a sub n plus 1, all right? So if we just sort of track this S sub n over here just to create a vertical distance, that distance right there, that is a sub n plus 1, that whole distance. All right, so if we're up here at whatever this number is, so this is S sub n, so we've added the first n terms. To get to S sub n plus 1, we have to add the a sub n plus 1 term to S sub n. We have to add one more term. All right, so S sub n is the sum all the way up to a sub n, and that's putting us above the sum of the series. So a sub n plus 1 is going to bring us down below. And that's what that distance represents, correct? If we look at the series that we had a picture of it, let's see, right, did I draw a picture of it? Or maybe I didn't actually draw the picture. Let's take a look at this one for a second, though. Let's look at this. So our alternating harmonic right here, S sub 1 is here at 1. So there's S sub 1. And then we subtract off a half, and we're going down to here. And then we're going to add a third, and we're going to bounce up. And the sum of the series is going to be right in here. That's natural log of 2 for the alternating harmonic. And so when we add, so we subtracted a half, and then when we add a third, we're going to be up here. And then when we subtract a fourth, we're going to be down here. And then when we add a fifth, we're going to be up there. So when you subtract the half here, right, this vertical distance is 1/2 from here to here. So if I do that distance, that right there has value 1/2. That's that length. Are you following that? And then when we add back up a third, this distance right here would be a third. So we keep adding positives and negatives to get to where we're going. And in general, if we're at S sub n and it's above the sum, the next term is negative. We're going to subtract the a sub n plus 1. And remember, with an alternating series, the a sub n plus 1, the a sub n is always positive, the a sub k, right? It doesn't include the switch. The switch is separate. In an alternating series, we treat the a sub k as positive. So here, S sub n brings us there. A sub n plus 1 is positive. We're subtracting it, brings us down to there. Here is the key point. This right here is the remainder, right? That distance is the remainder. The remainder is always the distance between the sum of the series and your partial sum. So that green distance is the remainder. Isn't that smaller than this distance, which is a sub n plus 1? Right? A sub n plus 1 is just the next term. So this is totally cool, because if we look at this alternating harmonic example, let's see, that's a K. So if we do this alternating harmonic example, first term is positive here, the way I've set it up. So it's going to be 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. And we know, I mean, we didn't prove this, but I've told you that that converges to natural log of 2. The alternating harmonic converges by the integral test, and it converges, not the integral test, by the alternating series test, and it converges to natural log of 2. So what this is telling us is this. So here is S sub what? If I add those two terms, S sub 2. This is A sub 3. No minus, right? No minus, or you just ignore the sign, right? So that's A sub 3. It's the magnitude of the next term. What this is saying is that S sub 2 is within 1/3 of natural log of 2. So if you just look at the magnitude of the next term, that gives you a gauge on the error. That's what this is telling us. So if we look at S sub 3, S sub 3 would be 1 minus a half plus a third. S sub 3 is within how much of natural log of 2? 1/4 of natural log of 2. And if we go one more, S sub 4, okay, that's the sum of the first 4 terms, which would be whatever that adds up to, S sub 4 is within how much of natural log of 2? 1/5. Alternating series is super easy to analyze the remainder because we just look at the first unused term. The first unused term gives us a great gauge on that remainder. The actual remainder is this. That's never going to be computable unless you happen to have a geometric series or something that you can find S. Like most series, we cannot find S. But we can say that, ooh, we're within 1/3 of S, or we're within 1/4 of S, or we're within 1/5 of S, or we're within 1/10⁴ of S. So in general, we can't if we could find S, then of course we could find the exact remainder, and the question is moot. But in general, we cannot find S, but we can analyze the remainder. And we can get it as small as we want. So that is our goal. So and when you get into a numerical analysis class or some other higher level math class that's going to talk more about infinite series in an engineering course or something, you'll do series in general, and you'll want to figure out how to find bounds on the remainder. But here we're just looking at the alternating series to really get the concept down. So here's an alternating series. This one starts at 1. So in my mind, I'm thinking about this. So we've got our alternating series, and tell me, is the first term positive or negative there?
It's going to be positive.
Positive, right? So this is the one we just looked at. So if we have our alternating series -1 to the k plus 1, and this one's going to start at 1, and this is 1/k. We just write out the terms, but I want to write it out generically here. So a sub 1 is positive, and then a sub 2 is also positive, but we subtract off a sub 2, and then we add a sub 3. So this is what you should be thinking in your mind. So that's looking like that. The a's are all positive, but then we add or subtract. So there it is. Now this says we want to find how many terms, and when they say how many terms, we mean the least number of terms so that the remainder is less than 10 to the -4 in magnitude. All right, so we want the remainder less than that. So what we know is that we want to figure out what k value satisfies this. So what we're going to do is say, okay, ignore your switch. We're going to take our a sub k. We want to know when is it less than 10 to the -4. If we can figure out the k value that's less than 10 to the -4, then we're just going to add everything that's in front of it. So if this term is less than 10 to the -4, then we can add up everything in front of it. Because if we add up everything in front of it, the next term is the gauge on the remainder. And if we want the remainder to be less than 10 to the -4, if we can find the k value that gives us a value less than 10 to the -4, we just add everything in front of it. So we want to find the first term that satisfies our remainder restriction. So we want to know, what is the k value that does this? So this is going to be 1/k less than, we'll write this as 1/10⁴. Cross multiply. So we're going to have 10⁴ on the left, k on the right. So 10⁴ is 10,000. So k has to be bigger than 10,000. So any k bigger than 10,000 is going to have a magnitude that's under 10 to the -4. So as soon as we get out past 10,000 terms, all of those terms are going to have magnitudes under 10 to the -4. We want the first one. We want the least number of terms that we can add together and have a remainder under 10 to the -4. So what is the first k value that we would use down here?
10,001.
10,001. So this tells us that we're going to choose k equal to 10,001. So we want to add everything in front of this. Okay? This gets back to, where did you start your counting cycle from? Did you start from 0? Did you start from 1? Did you start from 5? So this k is not telling us the number of terms necessarily. It's telling us the index value that gives us a magnitude under 10 to the negative 4. So we have to look at our scheme and figure out what's happening. So we've got our dots here. Let's just put a few terms around this. We're going to have an a sub 10,000. Would the a sub 10,000 have a plus in front of it or a minus in front of it?
Minus.
A minus. All the even indices correspond with a minus. So then we're going to have plus a sub 10,001, and then minus a sub 10,002, plus etc. Okay. So when k is 10,001, that puts us right here. This term is less than 10 to the negative 4. So that means if we add everything in front of that, we will have a partial sum that's within 10 to the negative 4 of the actual sum. In this case, natural log of 2. So we have to add everything in front. So we're going to add terms in front. So what we are going to add is a sub 1 through that one, a sub 10,000. How many terms is that?
10,000.
10,000, because we started at 1. If you start at 1, 1, 2, 3, 4, 5, whatever that last index is, that's how many terms you have. If you started at 0, it's a little different. We'll get to that in a minute. So, therefore, our conclusion is 10,000 terms. And we could write it like this. So if we're adding the first 10,000 terms, that's called S sub 10,000. And that would be, because we are starting at 1, the end term is 10,000. And this would be our partial sum. So that is within 10 to the negative 4 of S. Well, this happens to be a series that we know S. Like I said, in general, we don't know S, but that would be, in this particular case, we do know what S is. So there's our conclusion. We had 10,000 terms. The partial sum would look like that, and we'll be within 10 to the negative 4 of ln2. Let's try another one here. So this one starts at 0. We happen to know what S is because it's a special series that they were able to figure out the sum to. Who knows how? Same idea. Okay, there is our a sub k. Remember, a sub k doesn't include the switch. And we want this to be below 10 to the negative 4, so we could write it like that. Less than 1 over 10 to the 4th. We are going to cross multiply. So we'll have 10 to the 4th on the left. We'll have 2k plus 1 on the right. 10 to the 4th is 10,000. And we'll subtract 1, giving us 9,999. It's going to be less than 2k. So then we divide by 2. Remember that k is an integer. And so if you type it in your calculator, you know you're going to get whatever you're going to get. Just under 5,000, 4,999, 0.5 or whatever it is. So the first integer k value that will satisfy this is 5,000. Everybody okay with that? So now let's look at our generic scheme just to sort of make sure that we're counting properly. So k equals 0 to infinity here, and we have, I'm just going to call this a sub k here. We don't need to rewrite the whole thing. Put the switch in, put in a sub k. So the first term with k being 0 is it going to be positive or negative? Positive, right? Because k being 0 here gives us a 1. So we're going to have a sub 0 as our first, and then minus a sub 1, and then plus a sub 2, minus, etc. Now we're going to get out here. Let's put in a couple of terms around here. So we're going to have a sub 4,999. Should that be a positive or a negative in front of that term with an odd index?
Negative.
Negative. And then we're going to add a sub 5,000, and then we would subtract off a sub 5,001 plus etc. So there's the generic sort of look of our series. When k is 5,000, k being 5,000, so this is the k value right here, right? So this is when k is 0, when k is 1, when k is 2. When k is 5,000, we're right here. And that is less than 10 to the negative 4. So we want to add everything in front. We want to add these. Okay? So now we have to ask ourselves, how many terms is that?
5,000.
And that's 5,000 because we started at 0. So if we started at 1, that would be 4,999 terms, but because we started at 0, we have to pop an extra term on there. So we are going to add the first 5,000 terms. So therefore, 5,000 terms. And we would write this as S sub 5,000. If we're adding 5,000 terms, that's S sub 5,000. That's what S sub 5,000 means. This would be the sum, k equals 0 to 4,999 of negative 1 to the k. And if we write it out completely, we would have that. So there. And we would say, you know, this sum is within 10 to the negative 4 of pi over 4. So let me say that also, just to make sure we have some words here. So S sub 5,000 is within 10 to the negative 4 of pi over 4. So that's what that means. So we're pretty close to the actual sum of the series. We're within 1/10,000th, which is usually accurate enough. Now, if we're doing brain surgery, maybe not. Maybe we want to go a little further. But for measuring the amount of liquid in a container, that's usually plenty. Okay, so 5,000 terms. All right, let's try another. So these are a little subtle, take a little bit of practice. So here is another alternating series that converges. And these alternating series tests, you should kind of be able to see that they converge because we only have two conditions. We have that the limit of a sub k is 0, so a sub k doesn't include the switch. Like you can see, okay, yeah, these limits are 0. And these are decreasing. We know 1 over x squared goes like that, 1 over x cubed goes like that, right? These are going to be decreasing. Very easy to show. So, same idea here. We want to be 10 to the negative, less than 10 to the negative 4th. Let's move this. We need a little space. Okay, so we're going to start out. We want to know, okay, what is the k value that's going to cause this to be true? cross multiply. So we're going to have 10,000 on the left. We're going to have k squared on the right. Everything is positive, so we can take a positive square root. Square root of 10,000 is 100. So what is the first k value that satisfies this?
101.
Yeah, we're just going to say, okay, we want the first one. Certainly k being 2,000 or 150 or whatever satisfies it. We want the first k value. We want to minimize our effort. So we're not overachievers here. We just want the first k that's bigger than our condition here. So let's look at our generic series just so that we're counting properly. So we've got our switch, and then we have our a sub k. And this is going to start at 1. So we just want, this just gives us a nice visual. When k is 1, okay, that's positive, so we're going to start with a sub 1, not a sub 0 like the last one. And then we're just going to be alternating as we go through this. All right, and then we want to get around our neighborhood of this 101. So we're going to have an a sub 100, we're going to have an a sub 101, and let's go to an a sub 102 just with grins. In front of the evens should be a minus. So there's a minus, that's a plus, that's a plus. So that's what our generic description of this series would look like. This term right here is less than 1 over 10 to the 4, so it's less than 10 to the negative 4. So that is our remainder gauge. That is giving us a remainder of everything that's added up in front of it. So we add everything in front of it. So we want to add these. How many terms is that? 100. Right? Since we started our counting at 1, that index also tells us a number of terms. So we are going to add 100 terms. That is S sub 100. That's what S sub 100 means, right? It's the sum of the first 100 terms. So we would just go to 100. And then we can rewrite this exactly. Just try to get some practice. So we get that. And we would say that S sub 100 in our mind, where this is what we're thinking. So the words are sort of, in our mind, we're thinking, oh, okay, well, we're within 10 to the negative 4 of the sum of the series. Usually we don't know it, but they told us what it is here. Somehow they found it. So that is our conclusion. So the alternating series is sort of the simplest type of series where you can analyze the remainder in a really concrete way. And it's not hard, but you're definitely going to want to do some practice here with these indices. And I'm thinking on this one, I'm going to change this one. Let's make it more difficult. So let's change this. If we change this index, then we're going to change the sum of the series. So we don't know what it converges to. We'll just call it S. We don't know what S is. Let's suppose we start at k equals 5. All right, let's just make it as kind of general as possible. Just screw it up as much as we can, and let's see what happens. So first, let's write out the terms generically. So our first term is going to be, when we plug in our first index value, that's 5. So that's an a sub 5. And would I have a minus or a plus in front of that?
Minus.
A minus, because we're going to have an odd power on the switch. Odd power on the switch gives us a negative. So this is what the generic summation is going to look like. And we'll get to where we need to be in a second. So that's just sort of how it's starting, though. We're starting our counting at 5, not 0, not 1. Let's take our a sub k. So here is a sub k. We want that to be less than 1 over 10 to the 4th. Cross multiply. And we have this. Everything's positive, so we can take the cubed root of 10,000. That's not a known value off the top of my head. But let's just keep going. Let's finish the algebra. So then we're going to subtract 1 and divide by 2. So we're going to take the cubed root of 10,000. We're going to subtract 1. We're going to divide by 2. And k has to be bigger than that. So all we're going to do is type that into our calculator and find the first integer that is bigger than that. So let's just do that. So 10,000 raised to the 1/3 power. Subtract 1. Let's see, put some parentheses in here and divide by 2. And does that all look right? 3rd root of 10,000, subtract 1, so we get that. Let's just grab that thing. So we have it in here. All right, so what is the k value that we're going to choose then?
11.
Yeah, we'll choose 11. First integer bigger than that. So this is going to tell us that we have k equals 11. Black. Really? Touch gently. Why? I don't get you. So let's write it down here. So k will be 11. So that is our first integer that's larger than that expression. So let's go to our generic layout here then. So 11, let's get one before it, one after it. So we're going to need an a sub 10, an a sub 11, an a sub 12. In front of the evens is positive, in front of the odds is negative. So that's what the generic layout would be. So k being 11, so right here, this is less than 10 to the negative 4. So we want to add these. So the question is, how many terms is that? How many?
6.
So we have a couple of options here. In terms of counting, this one we can actually count on our fingers if we want, because it's so small. But here's what we could do. We could say this. So we want to add these. We don't know how many terms there are yet. But what we know is that if we did our index, we would start at 5. So k equals 5 to 10, right? And so we had a couple of ways to count there. One way was to do the upper number minus the lower number and add 1. The other option was to say to yourself, let's see, if I subtract 4 from the 5, I get to that nice starting value of 1. And if we subtract 4 from that one, we get 6. And if we start at 1, then the upper number is the count. Tells us the number of terms. So those are the two ways we could think about doing it. So 10 minus 5 plus 1, or subtract 4 there, subtract 4 there. So we know there's 6 terms. So the partial sum is then s sub 6, right? We're adding 6 terms. So that would be s sub 6. This would be negative 1 to the k. This is whatever our a sub k is. So s sub 6 looks like that. And that's going to be, that is within 10 to the negative 4 of, we don't know what s is anymore because we changed the series. So we changed the sum of the series. So we're adding 6 terms. So therefore 6 terms. The big question said how many terms do we have to add together? So that would be 6 terms to give us a result that's within 10 to the negative 4. This series has a 3 as an exponent in the denominator, so the terms are going to 0 really fast, so we don't have to go that far out. So we notice when that's a cube, we only had to go out 6 terms. When this was a square, we had to go out to 100 terms. So, and then, the other one before it, we had to go out even further when the power was just a 1. All right, so that's the basic approach to analyzing your remainder with an alternating series. Any questions on that? So, when you have an alternating series, there is one extra consideration. These terms, absolute and conditional, mean nothing when you're talking about series that have all positive terms. There's no distinction. Convergence is convergence. With alternating series, convergence is not convergence. So there are 2 things. When you have an alternating series that converges, you can either converge absolutely or conditionally. Those are the 2 types of convergence for an alternating series. If everything is positive, then you just stop right there. It's either converging or diverging. But if it's alternating, you can go one step further and classify that convergence. So here's what we do. Remember that with an alternating series, the structure of an alternating series is that you've got your switch and your a sub k. So remember that the a sub k is always positive in general when you're talking about an alternating series. Now, they're being a little bit sloppy here because what we have just said, and I've sort of tried to beat it into your head, is that with an alternating series, we think of the a sub k as positive always. So what I would have liked, here they're trying to be super general. They're just saying, okay, let's just suppose a sub k could be positive or negative. So here is an alternating series. Here is just a generic series. Might not even be alternating, but it has some negatives in it. So they're just trying to be general here, and they really should say a sub k could be negative. So they don't say it there. They should, though. So they're all of a sudden using a sub k not like we have been for an alternating series. All right, so for alternating series, if it's plus, minus, plus, minus, plus, minus, a sub k is always positive, and the switch is totally separate. Now, if we have a generic series where it could go plus, 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 then minus, then plus, then minus, 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 and then plus, and then so the minuses are not uniformly distributed as every other term. That's kind of what they're implying here. Not clear. So just in this case, they're not saying that this is an alternating series. They're just saying it's a generic series and a sub k is not necessarily positive. So a series will, so here's our series, the a sub k could be negative. So there's some positives, some negatives. That the most general type of series would have some positives and some negatives. So they're saying that that series will converge absolutely when you force everything to be positive. So you take the absolute value of every term. If that still converges, and it would have to converge to something bigger, right? If you have a series that has positives and minuses and you turn everything positive, that sum would have to be bigger than if you left some minuses sprinkled in, because the minuses are going to be taking away from the overall sum. So if you make everything positive and you still have convergence, then we're going to say that the generic plus minus, whatever, pluses and minuses, that series converges absolutely. That the minuses don't matter. So for example, when we look at the harmonic series, we know that this harmonic converges or diverges?
Divergent.
Diverges. But we know that the alternating harmonic converges. So the alternating harmonic converges to ln2. So what we would say is that this converges conditionally. Okay, so it converges conditionally because if we force everything positive, we get divergence. So the minuses, the only way it converges is it's conditional on the minuses. You need the minuses to be taken away. So that's sort of this is a good example to have in your head. Alternating harmonic, it converges by the alternating series test. We know that the regular harmonic diverges by the integral test. So we would classify this convergence as conditional. So another example. If we look at 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus etc. So that's 1 over k squared. Does that converge or diverge? It's a p series with p equal 2 that's bigger than 1, so we have convergence. So this is convergence. And if we take the alternating version of that series, do you think it's going to converge? Yeah, so we have a couple of ways to think about it. It's an alternating series and the terms are decreasing to 0 in magnitude. That's the alternating series test. That's all we need. So this would converge by the alternating series test. So what type of convergence would this be?
Absolute.
Yeah, absolute convergence, because if you take all the minuses and turn them plus, you still get convergence. So we're going to call that type of convergence absolute. So this alternating series converges absolutely, because if you look at the series of absolute values, you still have convergence. So it's really strong. Okay, so if you have a series that converges absolutely, that means that the series converges in the regular sense. So like right here, if we look at this series, that converges conditionally. So I'm trying to talk about absolute convergence. So let me rewind 5 seconds. So come down here. So if this series right here converges absolutely, we know that the series with the minuses has to converge. So if we have a series that has pluses and minuses, and we turn everything positive, and we get convergence, that means the series that had the pluses and the minuses must converge also. If you make it harder to converge, i.e. make everything positive, and you get convergence, then if you have minuses sprinkled in there, that's got to converge too. So if you know somehow that it's absolutely convergent, if the absolute values are converging, then if you took the absolute values away, it still has to converge. So if it converges absolutely, that means that the series without the absolute values also converges. Right? If you take the absolute values, that's making the series, that's worst case scenario. If you take everything positive, that's going to be the biggest possible sum.
Is that just the direct, not the limit test, the direct...
comparison test.
Comparison
Yes,
test.
that is a good way to think about it, because the terms in this series are going to be less than or equal to the terms in this series all the way through. Yeah. So if we have smaller than converging, we have convergence. Yeah. So, and equivalently, if we have the series that has some minuses sprinkled within it, if that diverges and you turn everything positive, definitely diverging. Right? So if you have some minuses in there and you get divergence, well, if you make everything positive, it's going to diverge even worse. Right? I mean, divergence is divergent. It's like, if you're pregnant, you're pregnant. But divergence, it's worse divergence. All right.
Worst pregnancy.
Right? Right. All pregnancies are bad. Carrying a baby sounds so difficult. Good result, tough process. All right. So let's take a look at this. Now, it's funny because on that last slide, like I spent a lot of time talking about this here, that this series up here is just sort of generically having some minuses. It's not systematically having like every other sign. But then all the examples that they give us that have some minuses are alternating. Because to create a series that would have a weird pattern of minuses is very difficult. You probably have to have some trig function with some weird period that could give you plus, 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 and then minus, 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 then plus, plus, plus. But to have it totally generic, 2 pluses and 1 minus, and then 5 pluses, and then 2 minus, like you're flipping a coin to get heads or tails, that would be extremely difficult to create a series like that. So the examples are going to give us are all going to be, just regular plus minuses. But you should be able to think in generality that if you have any minuses sprinkled without, you take the absolute value, you see what happens. So determine whether the following series converge absolutely, or conditionally, or diverge. So the first thing I don't want to write it down, but when we look at this, what test would we use to show that this series converges?
P-series. I'm sorry.
We will use P-series to test if it's absolutely convergent. But if we want to show that that series as it is, it's alternating, so we would use the alternating series test. So anytime we see an alternating series, the test that we want to use is the alternating series test. Now, what you said could be on the right track if you said to yourself, hey, well, let's take the absolute values, and if we take the absolute values and that series converges, then this series with the minuses converge, then that's a reasonable way to go. But in general, if someone throws you an alternating series to show it converges, you use the AST. And at this stage, let's just think about the AST as more generic. You think to yourself, these terms are going to 0. Right? The limit is 0, and the terms are decreasing. We know that 1 over a power of k is a ski slope going down to 0. So this series converges. Let's classify the convergence. So to classify the convergence, we are going to take the series of absolute values. So the series of absolute values is very easy to write down because the series of absolute values, you just take away the switch. So this is the series of absolute values. And it doesn't matter that it starts at 1 or 0. It does not matter here. So we don't even need to put the index. Now, like Caleb said, this is the P-series. How do we indicate that we know it's a P-series? We write P equals 2/3. We compare that to 1. So this is less than 1. Oops. Less than 1. So what does that tell us?
Divergence.
Everyone agree with that? So for a P-series, you're in the denominator. The power on P needs to be bigger than 1 to get those fractions to go to 0 fast. So bigger than 1, therefore it diverges. Oh. Okay, so that diverges. So therefore, I'm just going to say up here that this converges by AST. We won't write out the 2 steps. So we know that it converges by alternating series test. So how does this change that convergence? What do we say then? What type of convergence is that? Conditional. So therefore, conditional convergence. So if we end up with divergence for the absolute values, then the general series must converge conditionally. Okay, let's take a look at this one. So let's first decide, does that series, it's alternating, does it converge or diverge?
Converge.
Is there a specific type of series that this one is? Did I just hear it? Geometric? That is a geometric series. When you have a constant raised to a power, you've got that exponential look where the exponent is the thing that's changing, is variable. So this is a geometric series. So you can say that this converges because r equals -1/3 and the absolute value of r is less than 1. So this is geometric series. So it converges because we have a common ratio with a magnitude less than 1. Okay, so we've got a convergent alternating series. You could also use the alternating series test here, but because it's a geometric series, we could actually bypass the AST. So that's one reason. You could also say, or converge by AST. You take the limit of this, and it's going to go to 0, and the terms are getting smaller. As you multiply by 1/3 repeatedly, you're going to get smaller. It's going to decrease. So let's consider the series of absolute values. So the series of absolute values looks like this. So the series, and I should write that in general just so that it's obvious what I'm saying. So the series of absolute values looks like that. We just take away the switch. This, again, is a geometric series. R is 1/3, that's less than 1, therefore converge. Geometric series, I don't want to say by geometric series, I'll just say it converges and point out that it's a geometric series. When you say R equals, you're indicating that you know it's a geometric series, just like if you say P equals, you're indicating you know it's a P series. Okay, so we've got that our given series converges by one of these two methods. Then we have to classify that convergence. So does this converge conditionally or does it converge absolutely?
Absolutely.
So because the series of absolute values also converge, this converges absolutely. So if the series of positives converges, then we say the original series converges absolutely. All right, let's look at this one. So when we are thinking about this alternating series here, this one's a little more complicated, so I want to go through the process of showing that this alternating series converges. So let's do the steps here. Most of the times we've used algebra to show the decreasing piece. We've shown that a sub k plus 1 is smaller than a sub k. And that's a nice way that usually works great. But in this case, it's not going to work very nicely. You can just think in your mind, if you replace this k with a k plus 1, you would have to raise it to the 6th power. So you'd have to take k plus 1 and multiply itself 6 times. You'd have to use the binomial theorem or whatever to expand that whole thing. It would get really gnarly. So what we're going to use is the alternating series test, but we're going to use calculus to show the second step. So here's AST. So AST, remember, there's 2 steps. First step says take the limit of a sub k as k goes to infinity. This is an alternating series, so the a sub k does not include the switch. So we want the limit of this as k goes to infinity. And what is that limit?
0.
The limit is going to be 0. I want to do a couple of algebra steps just to make sure you're sort of remembering how this would be done if you wanted to do it really precisely. What we would do is turn the top into a square root also. And because we're dealing with positive k values, the square root of k to the 4th is k squared. I guess even if we were dealing with negatives, the square root of k to the 4th would still be k squared. And then you could pull the square root all the way to the outside. In other words, you could distribute the limit to the inside. And you'd have k to the 4th over k to the 6th plus 1. And so if we just went through all the gory details, divide everything by k to the 6th. Then on the inside, we're going to end up with 0 divided by 1, which is 0. So those are the sort of gory details of showing that that limit is in fact 0 as k goes to infinity. So now the next piece is more subtle. Again, if you tried to do it algebraically, it would be kind of a headache. We want to show that this is decreasing. We want to show that the a sub k's are getting smaller in magnitude. That's what we want to show. Doing it algebraically is kind of complicated, so we're going to do it with calculus. So what we're going to do is consider y equals, we're going to just turn all the k's to x's. So first off, I want you to think about this for a second. We could take the derivative of that function and show that that derivative is negative. Right? When the derivative is negative, your function is decreasing. When the derivative is negative. This looks like a real pitta to take the derivative of. We'd have to use the quotient rule. We've got a square root. It's kind of nasty. Or we could do this. So let me explain this. So what I did was similar up here. What I'm thinking in my mind is, if the function on the, you could think of this, let's see, where can I draw this? So look at these two places. So right here, so we've got this function, no, I don't want to look there. Let's see. I want you to look right here. So the function here, the bigger function is the square root of this quantity. You can think of it as the square root of another function. Right? You're taking the square root of, say, call this function f. And we're taking the square root of this function f. The square root function will be decreasing as long as this function is decreasing. If the inside of the square root is decreasing, then the square root of it must also be decreasing. So if we can show that the inside of the square root is decreasing, that means the square root is also decreasing. Okay? So if we have a decreasing function and we take its square root, that has to be decreasing also. Right? The square root of each number is getting smaller after we get past 1. Right? The square root of, if we have a function that's going down like this, if we look out here at the tail where those numbers are close to 0, the square root of 1/4 is 1/2.
Yeah.
So the inside number, if the inside numbers are going down, the outside numbers have to be going down. Does that make sense? Like if you look at, I might have just said that slightly in a convoluted way. Like if we look at, so if we call this function x to the -2, that's the red function here. It's decreasing. If we take its square root, that's the blue function, which is also decreasing. All right, So no matter what this function is, if you make this a decreasing function up here, make that a 6. So the red function's decreasing, you take its square root, you're still going to get decreasing. So that is going to give us just a little bit of a reprieve from a gnarly quotient rule. Because here the quotient rule is going to be very messy right here. So this has messy quotient rule. So if we consider that, if that function's decreasing, its square roots have to be decreasing. So that's the moral of the story. Okay, so let's do it. So y prime is low quotient rule, so low function, derivative of the high function, it's low d high, minus high, which is x to the 4th, times d low, which is 6x to the 5th, all divided by low squared. We've got that. So our whole goal is just to show that that's negative. Do a little bit of algebra in the numerator. We're going to end up with 4x to the 9 plus 4x cubed minus 6x to the 9, all divided by, same thing here. We don't need to multiply this out. So we'll go one more simplification step. We get negative 2x to the 9th plus negative 2x to the 9 plus x to the 3 times 4 all over this. Okay. Is the denominator positive or negative? Denominator is always positive. Everyone agree? Denominator is positive. We're imagining large values of x, positive values of x. Is the numerator positive or negative?
Negative.
That's going to be negative because we have our dominant term, the term with the highest power of x. This is dominating the numerator, and as x gets super large, that's going to take over these. These are positive for sure, the 4x cubed, but that's going to be way more negative. So we're going to get a negative over a positive, so that is negative. Therefore decreasing. So that's how we can show that this series up here converges by alternating series tests. So our conclusion here is therefore converge by AST. A little more complicated though because we couldn't do it algebraically. We have to do it with calculus. So a little bit messy. All right, so let's finish this off. We know it converges. The question is, does it converge conditionally or does it converge absolutely? So we're going to take our series. We're going to ditch the switch. So this is the series. I keep forgetting what's in the denominator. So we have that. So that is the series of absolute values. Series of absolute values. Do we think that this converges or diverges? So I hear a converge. What is the nature of this? Like if we get rid of this little plus insignificant 1, what's the square root of k to the 6?
K cubed.
K cubed. What is k squared over k cubed reduced to?
0.
K 1 over k. Right? K squared over k cubed. So the nature of this is going to be harmonic. So we're going to use the comparison test, and we're going to choose b sub k to be 1 over k, and this diverges because it's the harmonic. And what would we want to show if we are going to try to use this as our comparison series? What do we know? Do we want this a sub k to be bigger or smaller than b sub k?
Less. Wait, which one?
So b sub k diverges. So we suspect that this diverges. We call this a sub k. Do we want that bigger or smaller than the b sub k?
Bigger.
Bigger. Because bigger than diverging must diverge, smaller than converging must converge. Now, will we be able to show that? So this denominator is bigger because we have the plus 1, which makes the fraction smaller. So are we going to be able to use direct comparison? No. Right? If that was a minus, then we could. But because it's a plus, this is actually going to be bigger. So direct comparison is going to fail. So we won't be able to show it. Let's not go through the details of this. Can't show that. So the inequality is not what we want it to be. So what is our next step? If the direct comparison doesn't work, we go to limit comparison. So we're going to go to limit comparison test. We're going to take the limit of a sub k divided by b sub k as k goes to infinity. So that's going to be the limit of a sub k. That's the original. That's the one we're analyzing. That's the one that doesn't change. And then we divide by b sub k, which means multiply by its reciprocal. So let's go through the math here. That's going to be k cubed over the square root of k to the 6 plus 1. Again, the simplest way to get these limits is to do the square root thing. So make that the square root of k to the 6 over k to the 6 plus 1. And what is that limit? 1. What does that mean for the limit comparison test? So limit comparison test, if that limit is positive real, then both series do the same thing. So this is a positive real, so we'll indicate that like this. Therefore, we have convergence. Therefore we have divergence. Because the series that we compared to diverged. So they both do the same thing. So therefore we get divergence. So the big therefore, what is our final conclusion? Therefore, the original series, which was alternating, and we showed that it converged by AST, so we're classifying that convergence as conditional convergence. Yeah, that was a long one. So conditional convergence, the original series does converge, but it converges conditionally because if we take away all the minuses, we get divergence. Phew, time for a break. All right, let's take 10. I'll pause this, and anyone, if you have a question on any of those steps there, let's go. We can go over them. All right, let's go through this one. So let's do this one more completely. Let's do the alternating series test. So again, it's alternating. The one time, which we just saw a few minutes ago, that you may not go to the AST is if it happens to be a geometric series. Because you have the geometric series includes minuses, right? We can have that R value be negative. So you don't have to go to the AST if it's geometric. This is alternating, certainly not geometric, so we definitely are going to do AST. So the first step, remember, for AST, we take the limit as k goes to infinity of a sub k. A sub k does not include the switch, so it's just the limit of 1 over ln k, and that is 0. Denominator is increasing without bound. Numerator is constant. So first step, check. Now we want to show that this series, this series of absolute values decreases. So we want to show that as we go further out, the a sub k's are getting smaller. Again, the a sub k's don't include the minuses here. So this is a sub k, no minus. And it's pretty quick here. So a sub k is 1 over natural log of k. And a sub k plus 1 is natural log of quantity, k plus 1. We can cross multiply. We get that. Everything's positive, so we can exponentiate. Or if you're an Algebra 1 student, you can just cancel out the ln. And then we get 1 greater than 0, and this is true. So that checks. So therefore, we have a series that converges by AST. Now, we look at that series. We know it's alternating. So then the next question becomes, does it converge conditionally or absolutely? So we want to consider the series of absolute values. So the series of absolute values, that's how they are writing it in general, just to emphasize everything's positive. So we are going to look at just this. And what does that series do? It diverges. So remember, like when we think about a p-series is going to converge if the power on the k is greater than 1. So this denominator is going to infinity even slower than k. Right? So it's definitely going to diverge. And what we did when we showed this was to choose b sub k to be 1 over k. And we know that 1 over k diverges because it's harmonic. So we know that that's going to diverge. And so we want to show then, what do we want to show? Do we want to show a sub k is bigger than b sub k or vice versa? Bigger or less?
B sub k is bigger.
Bigger. B sub k series diverges. And we know that bigger than diverging will diverge. So if we can show that, then we know that 1 over ln k diverges. So a sub k is always exactly what we're trying to analyze. We don't know if this is true or not. We do 1 cross multiplication, and we get that. And this is true. And so we just look at the graph. There is y equals ln of x. And there is the graph of y equals x. So y equals x is bigger than natural log of x. So that is true. So therefore, we have divergence over here. So we have a converging alternating series, but we have a divergent series of absolute values. So what's our big conclusion then? Therefore, conditionally convergent. Conditional convergence. So, yeah, it's amazing because we have these series that, like this, where the terms are going to 0 so slow, but they are going to 0. As soon as you throw in that switch, you have convergence. If you have your series going to 0, the terms are going to 0, no matter how slow, if they're going to 0, if you throw in a switch, you have convergence. So alternating series test, all we're thinking about is magnitudes going to 0, and then it's going to converge. That's what the AST boils down to. Terms going to 0. All right. AST in the bag. Remainder in the bag. All right, now we have 2 more tests. The root and the ratio test. Now, the ratio test, of all the tests that we have had so far, this is going to be the most prolific going forward. When we get to the next chapter, which are called power series, which is basically an infinite series of functions, not just an infinite series of numbers, we are going to use the ratio test a lot. When you go on in other classes, when you come across infinite series, the ratio test is super common. So this one, of all of them, you really want to get dialed. Now there's something that's super easy about the ratio test, and that is its conclusion is identical to the geometric series. Geometric series, less than 1 is convergent, greater than 1 is divergent. And we've got this one extra thing that if R happens to be 1, it's inconclusive. So this is cool. So it's new, but it's not that new. It's going to line up exactly with the geometric series. So what we do is find this R value, this ratio. So we do this limit, the limit of the ratio of consecutive terms. So a sub k plus 1 over a sub k. And that's how we get this R. And if that R is less than 1, we have convergence. If it's greater than 1, we have divergence. Here is sort of an outline of the proof. If this limit is true, imagine being out in the tail of the series. So k is massive. Well, if k is massive, that means that R is approximately equal to this. So if k is super large, R is about equal to this absolute value. If the limit is R, that means this ratio is getting closer and closer and closer and closer to R. So if you're way out there, this ratio is about R. And if you multiplied both sides by the absolute value of a sub k, you would get that R absolute value of k is about equal to absolute value of a sub k plus 1's absolute value. All right. Isn't that geometric series? If you take the prior term and multiply it by a constant ratio to get to the next term, and now you imagine replacing the k with k plus 1 or the k with k plus 2, and it becomes a geometric series. So we're doing constant multiplication by R. So the next term is about R times the prior term. So it becomes this geometric series-like thing, and we know that geometric series converge if the magnitude of R is less than 1. So the meaning of this is that when you're out in the tail, R is about equal to the inside there. It's about equal to that ratio. Multiply both sides by the denominator. That's what geometric means. Geometric means next is constant times prior. That's geometric. And if you replace the k with k plus 1 and then k plus 2 and then k plus 3, this is true domino effect all the way down. So that's why the geometric series is going to come into play for the ratio test. So R less than 1, converge. Greater than 1, diverge. So let's try it. Let's try it. Now, the ratio test is awesome whenever you see a factorial. There was no derivative in this test. So we didn't have to deal with trying to take a derivative of a factorial or anything like that. Ratio test works beautifully when there's a factorial, because we're going to form this ratio of a sub k plus 1 over a sub k, and the factorial can cancel. So that's going to be super nice. So first off, let me point out one thing on the prior slide. So we've got a generic infinite series, the a sub k's. Here, we're not dealing with alternating. This is very generic. A sub k could have negatives in it. Could be negative. That's why they put this absolute value here. Some books will say, assume a sub k is positive, and they won't have an absolute value there. Here, they're being super general. So we've got this series, so a sub k could be negative. So might be negative. For some values of k. But notice that we're taking absolute value there. So that's going to wipe out any switch or any negatives. That's going to wipe it out. So here, so the ratio test, we're going to take the limit of the absolute value of a sub k plus 1 over a sub k. Limit of the ratio of consecutive terms. So this will be the limit of, and again, ditch the switch. That absolute value just takes away the switch. So a sub k plus 1, we're going to replace k with k plus 1. We're going to ditch the minus sign. So there's a sub k plus 1. And if we divide by a sub k, that's the same thing as multiplying by the reciprocal of a sub k. And again, we're taking absolute value, so we ditch the switch. And so there is what we have. We have to simplify the inside of the limit and take the limit. And this will be the R value. So how many 2's are we left with and where when we think about combining these two? 1, 2, and is it upstairs or downstairs? Up. Okay, so we're going to have 2. And I'm going to rewrite the k plus 1 factorial in the bottom as k plus 1 times k factorial. Because k plus 1 factorial, we do repeated subtraction by negative 1. And so k plus 1 multiplied by k factorial is one way to simplify that. And then the k factorials will go bye-bye. And what is this limit?
2 over k plus 1.
And so the limit as k goes to infinity? 0. Okay. Ratio test, just like geometric series, says less than 1, we have convergence. So that's it. Ratio test, absolute value of the ratio of consecutive terms. Take the limit as k goes to infinity. If you get less than 1, it converges. Greater than 1, it diverges. And if it's 1, you have to try a different test. Try another one. So here we're going to go limit. And this is, they call this R. So R is this limit. So R equals limit. Absolute value of a sub k plus 1 over absolute value of a sub k as k goes to infinity. So limit. So first we do k plus 1. Everything's positive here, so absolute value bars are unnecessary. So there's a sub k plus 1. Now we divide by a sub k, which means multiply by the reciprocal of a sub k. So that gives us that. How many 4's are left, and where are they?
1 on bottom.
So 1 4 in the bottom, 1 4 in that denominator. I'll factor it out to the front. Okay. Then we have k plus 1 squared over k squared. So we can do this a couple of ways. Let's write the numerator maybe as k squared plus 2k plus 1. Factor it out, FOIL it out. So we have that. And what is the limit of this part here? It's just that. What's that going to go to? To what? 1. Polynomials with the same power, limit is the ratio of coefficients. Or you could divide everything by k squared. If you divide everything by k squared, these two guys would go to 0 and you'd have a 1 and a 1. So however you think about it. Or you could use L'Hopital's rule. So the overall limit is 1/4. Then we compare it to 1. That's less than 1. Therefore, converge. Let's think about these intuitively. Polynomial over exponential. Yeah, convergence makes sense. Exponential dominates any polynomial, so the exponentials in the denominator, those terms are going to 0 very fast. Up here, exponential in the numerator, factorial in the bottom. Factorial dominates any exponential, so yeah, these are going to go to 0 very fast. So convergence makes perfect sense.
I have a question.
Yeah,
on
sure.
this one. So it was a switch, right? The
Yep.
number
Yep.
10. Do we have to prove if it's conditional or absolute, or is that only if it asks?
So this test takes the absolute value. So would this convergence be absolute or
Oh, absolute.
right?
Okay.
So this is going to be absolute, and it always will be with the ratio test because we are taking absolute values. Good question. So because we are taking the absolute value, this is actually detecting absolute convergence. So similar here, we're going to find our R value by taking the limit of absolute a sub k plus 1 over absolute a sub k as k goes to infinity. And so as soon as we take the absolute value, that switch is gone. So this is going to be the absolute value of a sub k plus 1. There's a sub k plus 1 in absolute value. And if we divide by a sub k, that means multiply by its reciprocal. So we get that. And pretty obvious that we have one extra 7 up top. We can factor it out to the front. And then we have k squared divided by k squared plus 2k plus 1. And what is the limit of this ratio here? 1. So our overall limit is 7. We compare that to 1. That's bigger than 1. So converge or diverge? Diverge. Yep. And this makes perfect sense when we think about our intuition. When we look up there, we have an exponential in the numerator and a polynomial in the denominator. Exponentials dominate polynomials, so that's not going to converge. That'll diverge. All right, you all try this one. Try that. know if you're snagged on any step. You end up with converge or diverge.
Diverge.
Does that make sense? If you look at the two functions that are being combined here, the numerator has the dominant function, so yeah, it should diverge. Those terms aren't even going to go to zero, right? So we could actually get away with using the divergence test. Could also get us there. Okay, but we are using the ratio test, and this one gives us a little practice combining factorials and powers of k. So I'm going to rewrite the k plus 1 factorial as k plus 1 multiplied by k factorial. And I'm going to just rearrange the denominator so we can talk about the different factors down here. Line up the factors with their like factors. Clearly the k plus 1s are going to cancel. Excuse me, the k factorials are going to cancel. And then one of the k plus 1s will cancel down on the bottom right. So we're going to end up with limit of k to the 6 over 1k plus 1 cancels, so we're going to have k plus 1 to the 5th. So here is the logic that I will use. You obviously could FOIL that thing out ridiculously. You could also use L'Hopital's rule a bunch of times. But we know that if you have a polynomial, the leading term dominates. So if we're looking at a limit at infinity, we really only need to consider that dominant term for that polynomial that's a fifth order polynomial. Right? This multiplies all the way out. You could use the binomial theorem if you wanted. This would be k to the 5th plus blah, blah, k to the 4th, k to the 3rd, k to the 2, k to the 1, k to the 0. And if you divide by the highest power of k, all those little terms at the end are going to 0. So it suffices to just sort of think about, if we're taking a limit at infinity and we're dealing with polynomials, we can just take the dominant term in that polynomial. That's going to dictate what happens. You can have a k to the 5th that has no bearing. If you have your k to the 4th, your k to the 3rd, your k to the 2, your k to the 1, your k to the 0, it doesn't matter how big the coefficients on those are. K to the 5th is always going to dominate 5 bazillion times k to the 4th, eventually. When you're going all the way out, and k can be as large as you want. The leading term is the only term that matters. And this limit then becomes a basic limit, a limit of k as k goes to infinity. And that, of course, is infinity, so therefore we have divergence. So that series diverges. And again, we could have also used the divergence test up there. Terms aren't even going to 0. So the ratio test, pretty straightforward. We love it. The root test also is lovable. So the root test is very similar. Instead of finding r, they call it rho here, Greek letter r. And we're going to take the limit of the kth root of the absolute value of a sub k. So this also is finding absolute convergence because we're going to be taking absolute values of all those terms. So notice the conclusion. Well, heck, it's the same as the ratio test. Same as the geometric series. If rho is less than 1, we have convergence, and it's absolute convergence because we took absolute values. And if rho is greater than 1, we have divergence. And once again, if rho is equal to 1, the test is inconclusive. We have to do more work. And this logic is very similar to the last one. Take a look at this. If you imagine k to be super big, if rho is the limit of the kth root, when k is really large, rho is about equal to the kth root. If the limit of the kth root is rho, when you go far, 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 far out, rho is essentially the kth root of a sub k. And once again, this is true for all k. And so that means that the k plus first root of a sub k plus 1 is about rho. And so we have a similar situation that we had with the last one, that out in the tail, this is just acting like a geometric series. It's like we're multiplying by rho repeatedly. So if we take this and we have that. So the kth term, absolute value of a sub k, is about rho to the k. And if you just keep replacing the k with, right, that's true for all k. So you can replace the k with k plus 1. You can replace the k with k plus 2. And we see that each term in the tail is about rho times the prior term. So once again, it has a geometric nature to the tail. The tail is geometric. And then our conclusion is, of course, the same as the geometric series, which is the same as the ratio test, which makes our life way easier. So, root test. When we see a factorial, we are going to lean into the ratio test. If we see a power of k on the outside, we're going to lean into the root test, because the power of k is just going to vanish when we take that limit. So we are going to take the limit, and this is rho that we're finding, not r. Some books will call both of them r. So the limit is k goes to infinity. And we're going to take the kth root of the absolute value of a sub k. So kth root, absolute value of a sub k. So when we take that absolute value of a sub k, that just gets rid of the minus sign. So the absolute value is going to ditch the switch. It's going to clear out that minus. So we're going to have the kth root of 2k over k plus 1 all to the k. All right, and the kth root of something to the k, they just cancel. So we're going to end up with the limit of the base, the limit of what's in the parentheses. So this is the limit of 2k divided by k plus 1. And what is that limit? 2. We are comparing this to 1. And we have conclusions just like the geometric series. If rho is bigger than 1, then we have divergence. All right, so that diverges. Are these terms even going to 0? That's my question. Like if we look at if we look at the limit, let's get rid of the minus sign and just, let me ask you this limit. If we have this,
No.
so the question is, are those terms going to 0? So this, the base here is going to what? Just the base. The base is going to
Infinity.
the base.
Oh,
2.
Sorry.
So the form here is a 2 to the infinity. That is not indeterminate. 1 to the infinity is indeterminate. 2 to the infinity is not indeterminate. So the only way we get an indeterminate form is if the base is going to 1 and the exponent's going to infinity. So this is not indeterminate. So this is the same thing as the limit of 2 to the k, and so that is infinity. So we could also, you could get around the root test by, going to this divergence test argument. But way simpler with the root test. Just take the kth root of this, take the absolute value of the inside, greater than 1 diverge. Root test is super clean. All right, try this one. You all try that one. So find your row and make a conclusion. Diverge or converge? Yep. Yeah, the root test, when you have a summand that just has that sort of power k on the outside, it really can simplify things down pretty quickly. So in our particular case here, we end up with the limit of the kth root of this. Isn't this just k over 2? Right? The kth root takes away the powers of k that we see in the numerator and denominator. And this limit, as k goes to infinity, is infinity. So therefore, we have divergence. I should maybe put in here greater than 1 in quotes. Right. Infinity, you don't really say greater than 1, but just to be, because we usually compare to 1. Anything bigger than 1, including infinity, will diverge. And that makes sense when you look at the nature of this. The numerator is a power tower. That's going to dominate any exponential. So no surprise. No surprise. That's going to diverge. So when we're dealing with roots, this question is going to show up a lot, ending up with the kth root of k. And it might not be obvious at first that this actually has a limit, and that the limit, if you look at this graph that I put up here from Desmos, looks like the limit is ostensibly 1 from the graph. Let's find the limit, though. So this is a sequence. When you plug in 1, you have the first root of 1, which is 1. Then you have the square root of 2. Then the cubed root of 3. The fourth root of 4. It's not obvious that that even has a limit. Not obvious. But we're going to use our log limit thing. So if we look at this function in terms of x's, we're going to say, oh, x, the x root of x. And then we are going to take the log of both sides. And when you take the log of the right-hand side, the exponent, which is 1 over x, right? This is x to the 1 over x. When you take the log of both sides, that 1 over x exponent can move down in front as a coefficient. All right, and then we take the limit of both sides. And when we take the limit of the left-hand side, we move the limit inside. And on the right-hand side, isn't it already in L'Hopital form? We don't even have to move anything. Right? Isn't that ln x over x, isn't that L'Hopital right away? Infinity divided by infinity. So this piece right here, L'Hopital's rule, because we have infinity over infinity, that's going to be the limit as x goes to infinity of, let's see, what's the derivative of the denominator?
1.
1. What's the derivative of the numerator?
1 over x.
So we have the limit of 1 over x as x goes to infinity, and that limit is
0.
0. So therefore, we end up with, so on the left we have this natural log. We're trying to get down to just the limit of y. So what do we do to both sides? If we want to move this natural log, what do we end up with?
Raise both to the e.
So we exponentiate.
Yeah.
We exponentiate and we get a 1. And so that's our limit. So the limit of this is, in fact, 1. So again, not obvious, but a pretty easy one to prove with our log limit process. And if we look at the Desmos graph, we can see that that makes sense. As x goes to infinity, these kth roots are approaching 1. Horizontal asymptote of 1. So on the exam, if you come across the limit as k goes to infinity, k through to k, if it's just in the middle of a bigger problem, you can now assume that that's 1. Like if the problem said show that this is 1 using the log limit process, then you'd have to go through that. But if you're just coming down to evaluating some limit at the end of a root test, you can now conclude that that's 1. So let's go ahead and do this one. So rho for root test will be the limit of the kth root of absolute a sub k. Now this one happens to be positive, so we don't have to deal with the switch or the absolute value actually. So we have a limit of the kth root of this. So let's make sure we're careful here. It's not quite as clean as the last one. So we have the kth root. So this will end up being the limit of the kth root of a sub k, kth root of k, excuse me. Let me write that a little more clean. So the kth root of k. And how about the denominator? What should be in the denominator?
E.
Just an e, because we have an e to the k raised to the 1/k, so the k times 1/k is 1. So that'll be just an e. And what is our overall limit then going to be? Yeah, 1 over e, because that numerator is going to go to 1. So we now know, and we can now use at our disposal, that that limit is going to 1. That quantity is going to 1, so the limit is 1. Then we compare this to 1. So with geometric series, ratio, or root, we always compare this to 1. Is this less than 1 or greater than 1? Less. So our conclusion, converge or diverge? Converge, yes. Perfect. So therefore converge. Yeah. Cool. Cool beans. All right, you all try this one with the root test. So we're going to take the limit. Rho will equal the limit as k goes to infinity. Kth root of all this. So limit of. Let me ask you this first. So the absolute value is usually pretty easy to implement. You see sort of the -1 to the k or something, or just a minus sign. Here we have to be a little thoughtful. Is this part inside here, so k is going to infinity, is this positive or negative?
Negative.
Negative, right? So we want to make that positive. And there is a way to make that positive. I'm going to write the word negative so it's a little, so that's negative. How do we make that positive without like putting an absolute value symbol in there? And if you multiply by -1, it becomes?
Alternate?
5k minus 1?
Oh.
Like, right? So if you have, if a minus b is less than 0, if you just switch this to b minus a, that's going to be positive. Make sense? If you multiply this side by -1, the negative b becomes positive b, the a becomes negative a, and you switch the inequality symbol. That makes sense? So if we think about a specific example, if we have something like 3 minus 5, that's going to be -2. But if we just swap it, we're going to end up with the same magnitude, but we're not going to need the absolute value bars. That'll sort of be the effect of having the absolute value bars. So in here, the absolute value of a sub k, we can do that by just doing this. So, and then we're going to take the kth root of that. So let me somehow get some brackets in there. So the kth root of all that. So the absolute value here, a little subtle, but we can get to it pretty easily by using this logic right there. Okay, so then we end up with lim. Kth root of this, those just cancel, so we end up with this. And that limit is 1/5. And then we're going to go ahead and compare that to 1. And that's less than 1, so therefore we have convergence. Can you tell me, if we look at this, if we were just sort of, if we looked at this, we've seen a lot of these problems where we have something that looks kind of similar to this, that's an indeterminate form. What is the limit of the inside here? So just inside the parentheses, forget about the k for a minute. What's the limit of what's inside here? Negative 1/5. That would be the limit of the inside. And so we have negative 1/5 to the infinity. That is not indeterminate. Negative 1/5 to the infinity is going to go to 0. Right, so this is not like a 1 to the infinity indeterminate form like we've seen a bunch of times. So that's not indeterminate. Okay, well, let's go to this page. Okay, so factorials. This says just choose your test. You know, we're in the root and ratio test thing, and so if you see a factorial, you just lean into ratio. If you see a power of k, you lean into root test. Pretty obvious which one to go with. So we're going to go with ratio here. So you have to be super careful with all these parentheses. So let's do that. Let's be careful. So k goes to infinity. We have the absolute value of a sub k plus 1 in the numerator, absolute value in the denominator of a sub k. Doesn't really matter. Everything's positive here. So a sub k plus 1. We're plugging in a k plus 1 for all the k's that we see. So we're going to end up with k plus 1 factorial. And all that is inside of a cube. So then this is going to be cubed. Is that okay? And in the denominator, we have to replace this k with k plus 1. That is going to be 3k plus 3 factorial. So do you see that? If you replace this k right there with k plus 1, that k plus 1 is sort of in parentheses. So that 3 would have to distribute to the k and to the 1, giving you 3k plus 3. And now we do the copy dot flip thing, or whatever it's called, the reciprocal of a sub k. So we have that. All right. Any questions up to that moment? Because if you're not clear on that step, then the rest is going to get really goofy. So we replace the k with k plus 1 up here. K plus 1 quantity factorial, and then cube that. Down here, replace that k with k plus 1, distribute the 3. So we're going to rewrite now. We're going to rearrange the denominator just so that we have the like factors kind of stacked. So first off here, we have seen a lot that we're going to just rewrite that as k plus 1 times k factorial. And then all of that is cubed. And then we're going to move this denominator over. That's going to be k factorial cubed. And then we're going to have the 3k quantity factorial. Now here's the one that's going to be a little different. We have 3k plus 3 factorial. We would like to rewrite it, expand it in a way that we can have some cancellation with that. So we have to think carefully here. So a factorial is repeated multiplication of factors where you repeatedly subtract by 1. So 3k plus 3, what's the next factor? 3k plus what? If we subtract 1 from this, what would we get?
3k plus 2.
Yeah. And then if we subtract 1 again, we get 3k plus 1. And remember that we can drop in that factorial symbol wherever we want, wherever it's convenient. So I'm going to keep subtracting by 1 And if I subtract by 1 one more time, then we have 3k, and that's where we're going to drop in the factorial. So we do repeated subtraction of 1, and we can stop wherever we need to, wherever we have a factor that's going to match with this thing in the numerator there. Now we have some cancellation. So that is going to cancel with that. And then over here, let's see, on the left-hand fraction, this is going to be a k plus 1 cubed. And don't these guys cancel? We have k factorial quantity cubed. Doesn't that cancel with this k factorial that also has a quantity cubed up there? So we just have a k plus 1 cubed in the numerator. I can make that more of a fraction, I guess. In the denominator, we have 3 factors remaining. 3k plus 3 multiplied by 3k plus 2 multiplied by 3k plus 1. So once again, we're dealing with a polynomial divided by a polynomial with a limit at infinity. And when we have polynomials, it suffices to look at the dominating term for each polynomial. So the dominating term in the numerator is k cubed. So this only works for limits at infinity. Down below, if you were to imagine foiling that all out, what would the leading term be? 27k cubed. Yep. That would be the dominant term down below. So this limit will have a value of 1/27th when all is said and done. We compare that to 1. Less than 1, therefore, converge. Yeah. I wonder if we can do this one in lickety-split. What test? Root or ratio? Root. Limit of, if we take the kth root of that, doesn't this just turn into a 1 minus 1 over k to the k? And what is that limit?
E.
Close.
Oh, e to the negative.
E to the negative 1? Because you can really make this a plus and there's a minus right there. So this is going to be e to the negative 1, which is 1 over e, which is less than 1, therefore converge. So as long as you remember that rule, 1 plus a over k to the bk will go to e to the ab. Then we'll get convergent. All right, let's stop doing math for now. We'll do more later. For sure, I won't let you down. We'll do more. All right, well, what, is this week 12 or 11 or something crazy? 11? Good grief. Good feel. I can't believe that we just finished the ratio test, the root test. It feels like, just feels like time is flying.